So on your equation sheet, on the far right-hand corner, not far right, middle right, is the small section for momentum. There's 4 equations for momentum. We're going to talk about 3 out of the 4 today. So momentum is this first equation, and it's a lowercase p, and p stands for momentum. Lowercase p, I have no idea why they chose the letter p, but it is. Momentum. Yeah, sure. There are 2 different units that you can use for momentum. Could be kilograms times meters per second, or another unit that is equally acceptable is Newton's seconds, or Newton's times seconds. Okay, so kilograms times meters per second, and that comes directly from our units of mass. M stands for mass, and mass is measured in kilograms, and V stands for velocity, and that's measured in meters per second. So if you take kilograms and you multiply it by meters per second, you get a kilogram meter per second. Where the other one comes in is actually down in this momentum impulse theorem, where force times the change in time is Newton's times seconds, or a Newton second. That's where those units are derived from. So just keep that in mind. A lot of times when they talk about momentum, you hear it talking about like collisions, and that's most of what we deal with is collisions when we talk about momentum. Right now we're going to talk about the change in momentum of object, but starting on like Monday of next week, we're going to talk a lot of collisions and interactions of 2 things. So what happens when 2 things collide? Well, they're going to interact, and what's the result of it? And that's where that 4th equation comes in. So that's a lot of times where we can hear. We also hear it in like as a sports analogy. You know, like, oh, the team just went on 10 on. They hit 5 baskets in a row going into halftime unanswered. They got a lot of momentum going in the second half. Or hey, by kicking that field goal right at the end, it really shifted the momentum of the team. So they often use it as an analogy a lot of times in sports references, but absolutely momentum is very crucial in most of our athletic things, like what happens when you run into someone in hockey or in football, or you kick the ball, right? That's in soccer. Those are all kind of the idea of this momentum impulse. But when we talk about change in momentum, on your formula sheet, it says it like this: change in momentum is equal to P2 minus P1. I'm writing this on the board because on the video that I asked you to watch by Bozeman Science, he derived the momentum impulse theorem from Newton's second law, and instead of writing as delta P, so this is what I refer to as the momentum impulse theorem. Delta P is equal to F times delta T, which is equal to impulse. That's how I have it written on your formula sheet. But the way he had it in his video is he didn't call it delta P, he called it M times delta V is equal to F times delta T, and then he had a box, and maybe these were reversed, I don't really remember. But the idea is the same thing. So P2 minus P1 is a change in momentum, while M times the change in velocity, that's going to be V2 minus V1. So it doesn't matter. You'd rather calculate it with using a change in velocity. That's fine. Just remember when you talk about change in velocity, it's V2 minus V1, final minus initial. Just like change in momentum is P2 minus P1. Okay, but that's the idea of a momentum impulse. So when we talk about impulse, it could be this or it could be this.
Broke up. You're lucky. You got real lucky.
Yeah, the marker actually like decapped along the way.
Look at my pants. It's a black mark.
Oh, is that really from the
You gotta be kidding me.
Oh, I'm sorry, Butcher.
What you looking for?
I'll be billing you. I got it. That's why I just came in quiet.
Yeah, definitely real quiet.
Okay, so,
With no issue.
impulse theorem. Momentum impulse theorem, I don't remember what it's in. Unigriffins, huh? Oh. Hey, did everyone, don't worry, Mr. DeBoer, the video was rolling the whole time. We got it on video.
I gotta go talk to Mike. I need a couple days off.
Maybe conveniently edit that out of the video.
Please do.
impulse. When we talk about impulse, the impulse momentum theorem, there's really, most of the time what we're talking about when we talk about this impulse is we really are focusing a lot of times on the force. And the reason why is we often, like just like in his video, he was talking about a car crash. Or in your example, where I asked you to design a device to drop an egg, we're talking about force, because the force is going to break an egg. If the force is too big, your eggshell will crack. So there's two things you could do to minimize this force. You could increase the time, or you could decrease the change in momentum. And how do you decrease the change in momentum? Well, it's the difference between this or the change in velocity. You got to get your velocity slower. Your initial velocity at the time of impact slower. And we'll talk about that a little bit. So there's there's three videos I'm gonna show you. The first video is of a car crash, two cars that they crashed together. It's by the Highway Safety Institute or Automobile Highway Institute. I don't remember exactly who it's by. But it's two different cars. So they take a 1959 Chevy Bel Air, which I'll show you here in a second, which is a big old car. So there's the 1959 Chevy Bel Air, and they crashed it into, and I don't know the speeds, a 2009 Chevy Malibu. So they're going to do a front-end collision, and they're going to kind of look at a few things. So let me pause this quickly. A couple things I want to mention is when we talk about collisions with cars, cars are things, and things can be replaced, right? So when we talk about car crashes, we want to emphasize that the emphasis should be on the occupants of the car. Okay, that's probably pretty well known, but I shouldn't need to say that, I should say. But keep in mind, so when we're looking at this collision, you want to be looking at the locations where the people are. You want to be looking at they only have drivers, in the drivers, right, the crash test dummies. So you want to be looking at like the dash, the steering wheel, the roof, the doors that would maybe keep them in, and kind of compare the two. In 1959, I think seatbelts were a thing. And you can say, what? I think seatbelts were a thing that were required to be in cars in 1959. I think. We could look that up, and I have in the past, but I forgot. 10 years later, I know for a fact that lap seatbelts were required, but they were still only lap belts. They weren't shoulder belts. But at some point, they became the standard equipment was a seatbelt. Prior to that, it was like a luxury item, or I'm not really sure. In the 59 Chevy Malibu, no, I'm sorry, not 59, the 09 Chevy Malibu, there's an airbag. That wasn't a thing in 1959 airbags. So as they collide, kind of keep those things in mind. In 1959, I'm going to make the statement that I think is a correct statement, that the bodies of the cars, the steel, the structure of the car was a thicker and stronger metal. And I'm pretty sure that's an accurate statement. And the reason I say that is two things. One, I just believe that. But two is my grandpa told me a story. And in 2000, I was driving, this is my story, I was driving on a slushy highway with my friend, my sister, and my now brother-in-law. And we were driving, and I thought I could four-wheel drive, I was passing a car, figured, whatever, I got four-wheel drive, lost control of the car, rolled in the farmer's field, and we all walked out unharmed. We were okay. However, my parents' car, which was less than 9 months old at the time, was completely totaled. So, felt bad about that. I was very shaken by the fact that I was just in a pretty significant accident and emotionally. And I didn't want to drive for a while. So my grandpa, who I think was trying to cheer me up, I believe that was the moral of his story, or the intent of his story, I should say. he told me a story about back when he was a boy, one of those stories, you know, on a Friday night, me and my buddies went out driving, and it probably was preceded by we put a nickel's worth of gas in, or a quarter. There was always something along there, like, we could put a nickel's worth of gas in and drive all night, or a quarter maybe it was. Back when it was only a nickel at the gallon, something like that. But him and his buddies were out driving one night, and he rolled his dad's car. So I rolled my dad's car, he rolled his. We're connecting here, right? Hey, he's telling me a good story. And he's like, but you know, we were all fine too, so that's good. Everyone was unharmed. And I'm like, and he's like, but my dad never found out. And I'm like, what do you mean your dad never found out? Yeah, I rolled my dad's car, but he didn't find out. I'm like, what? He's like, well, yeah. So we rolled in the ditch, and we just pushed it back on its wheels, and we drove home. I'm like, what? He's like, yeah, me and my buddies, we just pushed it back on its four wheels, and we drove home. And I'm like, and you didn't tell your dad? He's like, well, no, he was kind of mad because like the side view mirror broke off. But other than that, there wasn't any damage. So maybe the speeds were very different, I'm not really sure. But the combination of I totaled my parents' vehicle versus he broke off a mirror and never told his parents about it. By the way, you should be honest with your parents and tell them things like that. But anyways, he broke off a mirror, and the bodies were built a little beefier. The metal is thicker, right? I accidentally dented my parents' door one time with my knee. I was climbing in and I went wham! I'm like, oh, that hurt. But later I'm like, oh, that's where my knee was, right? So I don't think you could do that with a 59 Chevy Bel Air. But the thing is, when these two cars collide, again, we're looking for like the door, the dash, the roof. Those are things we're really focusing on. And there will be like one of the camera angles will be actually right in the back seat of the car, on which you get the best. But again, roof, door, the seat, you can actually see the back of the seat in a different angle. The dash, the steering wheel. There's one more angle that you can kind of see the dash best, but there's one more angle of the 59. So now you can really see the dash on the roof here. Okay, the seat shifted, everything. Okay, so again, the important when we talk about collisions is the occupants of the vehicle. Now here's an 09 Chevy Malibu, airbag deployed, as you can see, shoulder belt also. I think there's only two. Yeah, there's only. Again, watch the seat, the dash, the roof. And I'll say, and I'll make the statement. Besides the exception of like glass breaking, seats kind of jerking, that's a relatively unchanged location, right? The box where the driver is relatively unharmed. Compare that to where this driver is, like here's the front end, here's their knees, okay? So the idea is with now today technology, they have what they call the crumple zone. So this part they try to keep very solid, but they purposely design the front end of the car to crumple or to smash. Now, why would they do that? The intent of that is for when we talk about these changes in momentum, your change in momentum in this car is the same. You're going from 65 miles per hour, 55 miles per hour, 35 miles per hour. I don't know what this crash is taking that, to a stop. Your change in momentum when you're in this car is going to be the exact same. But if you can increase the amount of time it takes you to come to that stop, the front end of your car crumples. That's increasing your time that you're stopping. The seat belt, the airbag that is cushioning your head, also preventing you from smacking the steering wheel, but it's increasing the time. By increasing the time, we can decrease the amount of force. So the momentum impulse theorem we talk about a lot when we talk about collisions. And your egg drop was really just a giant NASA experiment. I shouldn't say an experiment. It is very similar to something that NASA has done, just on a much bigger and more expensive budget. Okay, this is an animation from a Mars rover by the name of Spirit. Yes, this is Spirit. Spirit was one of the early rovers. This is not, for the record, the rover that will be landing around 3 o'clock tomorrow on Mars. That's the one called Perseverance. I'll show you that video a little bit. The idea is rockets, hey, going really, really fast. lots of burners. We got to escape the Earth's atmosphere. And then we can use this thing called inertia, that once an object is in motion, it tends to stay in motion unless acted upon by a net external force. So once we're in space and we're going, we don't have to keep rockets burning the entire time on our mission to Mars. The rover that's about to land in Mars has been traveling towards Mars for about 7 months, I think it's been. It's been on that path for 7 months. And in those 7 months, they haven't had to use their jet engines because they set the course and they're just flying. Right? Now, if you watch this, they purposely make this thing spiral much like a spiral of a football is for stability. Okay, so you can take and shoot a rover into space and have a better path by spinning it. It's called angular momentum, and it will fly straighter and truer than if it were just to be like a knuckleball floating through space, right? That's kind of the analogy. So once it's going towards Mars, we just kind of let it, I talked over it, but it says we don't need to fire the rockets for the entire time. Right now, at least yesterday, I haven't looked today, 300 million miles, 7 months later, okay? So it takes about 7 months. In 7 months, it's as of yesterday, it was going about 47,000 miles per hour, the rover was. 48,000, something like that. Shoot, I was that far. Okay, so now we're getting near Mars. There's an atmosphere on Mars, just for the record. There is an atmosphere, so it means there's going to be friction. Okay, so that friction is going to increase air resistance, which we often ignore. Really is a thing, especially when you're moving like 48,000 miles per hour. It's going to slow this thing down. Okay, and as long as it doesn't, it has good heat shield, it should be okay. Okay, and then what happens is it takes a lot of that energy, it's slowed down. I think they're going to say, I'm talking over it, I know, right around 11,000 miles per hour, it's still going. Now they pull a parachute. Now this is a special parachute. It's not just like the one that you go skydiving in. It's really, really strong. It's called a supersonic because it's going faster than the speed of sound. So it's still coming in really, really fast. And again, the idea is you got to try to make this rover that you just spent billions and billions of dollars on and spent months and months and years of design getting there to not crash and bust up because the force is too big when you get there. So another parachute trying to slow it down a little bit further. And then they had this great idea that what if we just put a bunch of airbags and we just bounce it along the surface? So we have some retro rocket boosters to try to slow the thing down a little. And then yes, that is exactly what they did with the Spirit rover. They bounced the thing along the surface. I would talk to a NASA engineer. I didn't talk, I guess, I was at a speaker. I heard him talk at a presentation of one of the engineers that was part of the Mars rovers, Spirit and Curiosity. And he said, like, there was a pretty good potential that one of these things could have popped on a rock, and that'd be bad. So they tried to pick the non-rocky areas, but the problem with choosing a non-rocky area is that's kind of the area they did want to like look at, because that's kind of where the good stuff is. Like, if you just pick this place without a lot of rocks, then maybe not going to be what we want to research. And then it bounced, and every time it bounced, it slowed down, and eventually it landed. So the idea is, in order to minimize this force, they did a couple things. They increased the amount of time impact. They bounced that thing along the ground a lot of times. And they used a parachute to slow the change in momentum, make that small. They used retro rockets to slow that down, okay? And then they bounced it along the ground. Much like your egg drops. A little bit like your egg drops, okay? Some of you cushioned it. So when it bounced, right? It increased that amount of time. I don't remember if any of you attached like a parachute type device, but you could, right? And if you were to create a parachute thing, it should hit the ground slower, which therefore shouldn't break. My son got all excited by looking at your guys' pictures, and my daughter did too, so they tried to build one, and my son chose to do a parachute out of a shopping bag, but when you drop it from this high, the parachute doesn't have enough time to really do a whole lot, and it still went thud. Okay, so that was the Spirit rover. Spirit, yeah. So the guy who talked, he's like, I designed that. He was all proud at that moment, because he deployed the mechanism to deploy the solar panels. Okay, so that's that one. And then they hit so believe it or not, one of the big things that they were really worried about is would they be able to roll it off of that platform? Because if they can't, now they're kind of stuck. They can't really do a whole lot just sitting there. But it did. They were able to successfully roll it up. So that is Spirit. Now there's been another one called Curiosity. The one that's going to land tomorrow is called Perseverance. It's similar. There are some similar things, but they decided not to bounce it along the surface like they did with Spirit, but some of the same ideas are applied. The animation he showed, the NASA scientist showed at the seminar that I was at, had one that was for, I think it was the Curiosity rover, which landed pretty much the same. But again, same idea, coming in fast, 40-some thousand miles per hour, entering the atmosphere. Lots of friction. Friction slows you down, causes unbalanced force, which creates acceleration, which is coming in hot. Get it? Hot, literally. Wow. Thank you. Okay, so that might have been his joke. I stole this for the record. I don't remember. Credit to the NASA scientist or the engineer. I don't remember. They're trying to land it in a crater this time. So as they've gone through and landed these, they're like, hey, we're hoping to land it in a target like this big, and now this big, and now this big. Now they're trying to actually land it inside of a crater because they think then ancient life, we're looking for ancient life. In the crater was probably a lake at some point, so they're looking for some ancient like life forms. This was kind of cool. They actually have a drill. The last one did too. They had a drill that they could take some samples and test it on board. Where this one, it has a core drill. So they just dropped the heat shield, by the way. He described this as Iron Man. They're doing the Iron Man thing to try to slow it down. So now they're gonna. This is all like computer, like well, this is computer animation, but this is all done by computers. There is not a person piloting this thing. Okay, this is all fully automated. And then if they were to land this thing like this, there'd be so much dust and debris thrown around that it'd like cover the thing and like get it all dirty. So they decided that instead of like landing it like that, they should just lower it by a rope. I think that's like a 20-some foot rope. They cut the rope, and then that thing just flies away and hopefully doesn't land on top of the rover that they just dropped, because that'd be bad as well too. And then that thing just goes and crashes somewhere, and then there's the rover. This is Perseverance. Now this one has a drill on it as well. The thing about this one, it has a core sample. It can drill like core samples, like little chalk-sized things. And I don't know when they plan to do this, but the intent is to take those samples and pick them up on some other like space mission, and then send them back to Earth so we can analyze them here on Earth. You can say, well, why wouldn't they just analyze them there? Because our technology that we can have in the science lab, not this science lab, is way better than we can put on a probe and send millions of miles away, or thousands, I don't know how far away it is. But that whole process is fully automated. It takes, they call this 7 minutes of terror, I believe is the term that they use, because that whole entry sequence takes about 7 minutes. And during that time, a lot of things can happen. But they are not flying it, and the reason they can't fly it is because even at the speed of light, which is what radio signals send, like, hey, turn left, turn right, turn left, turn right, more power, less power, one-way signal takes 12 minutes. So if you say, hey, turn left, it takes 12 minutes for that, it would take 12 minutes for that thing to respond to turn left, which would be delayed at that point, right? So there's a lot of ground sensing radar in order to do that. So it's the same thing when they drive the rover. They like program the sequence of like, hey, go this way. The thing that's a little interesting, I guess you could say, is they can go through and like, what if they come across a rock and they're like, oh, what are we gonna do? Well, it moves about 0.1 mile per hour. So they got some time to kind of figure that out. Be like, oh no, there's a rock like over there. What are we gonna do in half hour when it gets there? With that said, there's like 6 articulating, not articulating, that's not the right term, but 6 wheels, all independently driven, 4 of which can steer, but they can actually climb like boulders about knee high is what they can climb over. It's designed to like withstand a 45-degree tilt without rolling over, which would be bad because you can't just go and like pick it back up if that were to happen. So but that idea is kind of a little bit what your egg drop was. And if we can minimize the amount of momentum coming in, slow it down before the impact, parachute maybe, or if we can increase the amount of time, that's the cushioning idea, then we hopefully can prevent our rover on Mars from breaking or your egg from cracking. And that's kind of the idea of that momentum impulse. So let's take a look at that worksheet that hopefully you grabbed on the way in. The worksheet on the way in is called in-class momentum. There are 8 problems that we are not going to go through today. We are going to go through 2. Maybe we're going to go. Okay, so we're going to go through problem 1 and problem number 2. If I were to ask you to calculate momentum, and this is something I don't think I mentioned, momentum is a vector quantity. I'm pretty sure, I think the guy's first name is Paul. I'm trying to remember. Mr. Anderson from Bozeman Science, that YouTube video that I asked you to watch. He mentioned it, and he mentioned that velocity is a vector quantity, and velocity has a direction associated with it. And he used like this little arrow over it. Momentum is also a vector. So when we talk about momentum, we also have to include directions. And those directions that we get from momentum, positive and negatives, come from the velocities being positive and negatives. So we're going to follow the same convention that we did in 1D and 2D motion. And we're going to talk about objects moving to the right have a positive velocity, and objects moving to the left have a negative velocity. Or objects moving down are negative, objects moving up are positive. We're going to follow that same convention. So pictures are pretty good. This first problem is going to talk about what is the ball's change in momentum. And this calculation is one that time and time again, if I were to ask a question on a test like this, hint, hint, people get wrong, okay? So it says a 0.2 kilogram ball is thrown at a wall at 0 meters per second to the right. So I'm giving you the direction. It bounces straight back at the same speed. What is the ball's change in momentum? I'm asking for the change in momentum. Now there's 2 different ways you could calculate change in momentum. I'm going to show you one, but I'm going to use that equation. That's the one I've used in years past.